Hello, BC Calculus students. So we are really getting to the end of things here, but today we are going to take one of our last 2 days here with trig substitution, and we are going to learn a different thing to do with trig substitution. So it's still trig substitution, it's doing all the same things we've been doing, but we're going to learn how to use completing the square together with trig substitution to solve, once again, more types of integrals that we might not be able to do otherwise. So let's go ahead, let's take a look. So there's really no new learning other than just looking at how we combine these two things together that you already know how to do. So here's our integral. So it is the type of thing that we notice right away. We've got a square root, and so it's an integral of a square root, and there's a squared underneath it. So we tend to think right away, okay, this is the type of thing that's a trig substitution, but it's not the general form. It's not something where we have a u squared minus an a squared or a u squared plus an a squared. So we're kind of left to have to try to do something a little bit different. But what I'm going to do is I'm going to use I'm going to use completing the square to get it into the form that I want to have in order to use trig substitution. So what I'm going to do is, and this is a review a little bit of completing the square. So the first thing I'm going to do is I'm just going to, for convenience sake, so you can see what I'm doing, I'm going to break this apart. Notice this is still exactly the same thing as this. I've practiced a little social distancing here. We have moved the 3 outside of this, so it's moved it 6 feet away from the rest of this, just giving us a little bit of room there. And what I'm trying to do is get this to be a perfect square so that I can express it as a square rather than just as a polynomial. So what I'm going to do next is, notice I'm going to take half of this -4, which is -2, and I'm going to square it. -2 times -2 is +4. So I have this +4. But if I just added 4, in order to keep it the same thing as this, I have to also subtract 4. So I'm going to subtract 4, but notice I want this to be the perfect square, so I add the 4 here, I subtract the 4 there. Now, it's the same, it's still adding 4 and subtracting 4. It's going to have the same value, but what has happened here is I can re-express this now as a square, and I take the 3 minus the 4, and I get a -1. And so now I get it in the form that I'm used to seeing for trig substitution. So what I'm going to do here is I'm going to do a little u substitution, let u be x minus 2, which makes du dx. So now I can go ahead and change it into the form of u. And what I have here is a classic case for trig substitution. And I hope that you recognize at this point here that this is one of our special cases where we memorize what the integral would be, or at least we know that we look at that one to get that, because we don't want to go through the time to do this. We can, but remember, it's that real long process that took me basically a whole page to do, so we don't want to do that. So what I'm going to do there is I'm going to simply memorize that this is 1/2 times our u times the square root of u squared minus 1 minus the natural log of, and I have the absolute value of u plus the square root of u squared minus 1 plus our constant. Of course, from here, we need to resubstitute back in for u. So substituting back in for u, because once again, we want it in terms of x, I get this. So notice here, so substituting in for u, I get x minus 2. In here, when I substitute here, notice my u was x minus 2, but remember, x minus 2 squared minus 1, that was just a reworking of this. So really, that's just that expression I started with under the radical, minus the natural log. My u is x minus 2 that I have there, plus, and once again, this is just a reworking of this original, so I can just put it back to the original, and now it's all in terms of x. All right, so that's one that allowed us to see how to use completing the square. Now let's look at one that's a little more challenging type of completing the square, and also one that's not just one of our special forms. So here's our second example, example B. So now we've got something like this. Now at first you may tend to think that, oh, this may be one of those inverse trig, but it's not. So alas, we're going to have to do it a different way. So what I'm going to have to do is I'm going to have to use the completing the square. So the first thing I have to do is I'm going to rewrite this in the way I'm used to seeing. So I'm going to put the 6x squared first. And notice now, remember, I don't know if you remember exactly what to do, but I've got a constant in front of the x squared. This is more difficult to deal with than before, where there was no constant in front of the x squared like this. When there's only a 1 in front of the x squared, it's much easier. So what I have to do is I have to factor that 6 out because I've got to have a constant of 1 in front of my x squared. So factoring out that 6, I get this. I think you can clearly see if I multiply the 6 back in, I would get right back to this. But now what I'm going to do is this is multiplication under a radical, so I'm going to break it up, but I'm going to just bring out that radical 6 so that I have the following expression right here. And now with this one, I can go ahead and I can do my completing the square magic on that one. So I'm going to take half of 1/6. Half of 1/6 is 1/12. 1/12 plus 1/12 is 1/6. And I will square the 1/12 and get 1 over 44. So I am going to write this as the following. Notice when I add the 144, this becomes a perfect square here. And of course, if I add 144 and subtract, it's still the same value. Re-expressing this part as the perfect square, I get the x plus 1/12 squared minus the 1 over 44. Now from here, I can go ahead and use trig substitution. First, I have to do a simple u substitution. I'll let u be my x plus 1/12, which makes my du dx, which lets me then re-express this whole thing as 1 over radical 6 times the integral of du over the square root of u squared minus 144. So from right here, this is not one of our special forms, so we build our triangle. So building our triangle, notice the u, since it's u squared minus the 1 over 144, has to be the hypotenuse. I make my constant side here the adjacent, and then that makes this radical expression be the opposite. Okay, now the first thing I need to do is I need to be able to replace this, so I'll solve for this. I want to compare this with the constant, so I know that that would be the tangent here. So the tangent of theta is equal to this square root of u squared minus 144 over 1/12. So if I want to get this by itself, I will multiply both sides by 1/12. So I will get that square root is equal to 1/12 tangent of theta. And I'm going to also have to know what u is, and so I can get my du. So my u in this case, if I look at my u, remember I'm trying to change it all in terms of theta. So my u, if I look at going to compare these two sides here, which is going to be, make this in the numerator is going to make it secant. So I know that I got u is 1/12 secant of theta. And then taking the derivative of u, I would get 1/12 secant theta tangent theta d theta. So now I can go ahead and I can do my classic trig substitution and substitute in. And so I've got my 1 over radical 6. My numerator is my 1/12 secant theta tangent theta d theta. My denominator is 1/12 tangent theta. From here, notice my tangent thetas cancel and my 1/12 cancel. So I'm just looking at 1 over radical 6 times the integral of secant theta d theta. Now at this point, I think I've integrated secant theta enough that you should know how to do this and either be able to do it or maybe even have it memorized because we've done it enough. So we know, you should know that you multiply both the top and bottom by secant theta plus tangent theta. And when you do that, then you let u be the bottom of secant theta plus tangent theta, and your top is your du, and so you can go from there. And then when you integrate that, you get this 1 over root 6 times the natural log of the secant theta plus the tangent theta. And I'm not sure why there is a d theta there. That is not supposed to be there because we've integrated, and that means it's gone. So I don't know how it snuck in there, but it did. And so we will get rid of that. That looks better. So now I must get rid of the thetas and get it back to x's. So the first thing I'm going to do is when I replace, I end up replacing in terms of u. So notice the secant of theta, solving for secant of theta, multiply both sides by 12, and I get 12u, plus the tangent, going back up here and looking at the tangent of, I notice that the tangent of theta, I would have to go ahead and multiply both sides by, in other words, if I want to get, what was I looking for here? Oh, tangent. If I want to get tangent by itself, if I divide this by 12, by 1/12, that's the same thing as multiplying by 12. So I get that it's just going to be 12 times that square root plus c. Now I do want to get it back in terms of x. So going back, if you remember that u, back when we very first substituted on this, we saw that u was x plus 1/12. So now I will put in x plus 1/12. Notice if I go 12 times x plus 1/12, I got 12x plus 1. And then this plus 12. And then notice that this, if I look here, this u squared minus 144, remember that's all just a way of simplifying down. You notice when I got that right here, that right here was a way of getting, that was this. And then this actually came from this, which actually came from this. So I know that that is just going to be the square root of x squared plus 1/6 x. And that's a good final answer. I can stop there. I've got it all in terms of x. Looks pretty good. But if you want to, you can go a step further in simplification, and you can get rid of this 1/6 here. And what you have to do in order to do that is you have to basically say, hey, I want to multiply by a 6 in here, which means I have to multiply this whole thing by a radical 6 so that I can bring the 6 in and distribute it. So to multiply by a radical 6 would mean I would need to compensate by, if I had a factor of radical 6 over radical 6, brought that in, I would get 12 over radical 6. 12 over radical 6 would go ahead and it would reduce down to 2 radical 6. So I can re-express this as 2 radical 6 and then get back to my 6x squared plus x under the radical. So this is actually the best form, but I certainly would not, I would certainly give this full credit like on a test or something like that. But probably if it was a multiple choice question, that would actually be what the answer would look like. Okay, that's all the completing the square stuff we have. So I hope it's going well. We have one more thing to look at next class. And then it'll just be the final on Friday at 8 o'clock. So I believe it's going to be through AP Classroom, but it will be one of those things where you will be logged into Zoom the entire time you're doing it, and you will be on a time schedule, and we'll all be doing it right at 8 o'clock on Friday. So hope things are going well. Let me know if you have any questions. Homework is 43 through 46. Yes, all 4 problems. And the truth is, I probably shouldn't admit this, but I will. There's actually only 2 of them that you have to use trig substitution. I believe there's 2 of them you can actually do straight if you want to with u substitution. But if you want to try one with trig, you're welcome to do trig as well. Okay, hope it goes well.